Hi, good morning. So I'm here to talk about my research on hunting and disrupting DNS-C2 and tunneling inside Linux kernel, the stealthiest process and the stealthiest C2 channels at scale in cloud. A bit background about myself. My name is Vedang Parasnes. I'm an independent researcher, a recent former master's graduate from University of Washington. My research interest focuses on Linux kernel security, kernel hardening, eBPF, and its intersection with user space, AI, and cloud to build endpoint security solutions that solves emerging problems. I'll try to structure the talk into four main parts. I'll start why DNS is a critical backdoor when it comes to command and control, and why most of the advanced persistent threats prefer DNS as a communication channel when they exploit your cloud environments. Then I'll talk about some of the attack vectors and the C2 infrastructure, how C2 IPTs are scaling their command and control infrastructure to compromise your networks. Existing approaches and the challenges for the preventing these emerging attacks. And then I'll present a research, AI-driven kernel-enforced endpoint security, and a cloud deployment architecture, how that can be deployed in the cloud environment so that you can come back to your remote scaled C2 infrastructures. A short demo of breaking down Sliver C2, DNS-C2, a well-known adversary emulation framework. And we'll conclude with key takeaways and future direction. Every time, most of the advanced persistent threats, DNS is a preferred choice for their communication channel. And that DNS is the preferred tool in their arsenal. This diagram shows all the advanced persistent threat over the last decade. If you could see, Wall Typhoon, the recent Chinese powered APT, had DNS beaconing inside it. And it used DNS for exfiltrating and maintaining persistent control. There are other APTs as well, like some of most famous, like the Cozy Bear, a Russian-powered APT, as well as the Ocean Lotus, which is a Vietnam government-powered APT. All of them, they compromise, the damages to DNS-C2 and tunneling are massive. They compromise national defense from infrastructure to hyperscalers, mission-critical environments, breach data, as well as harvest credentials at scale. As per the Unit 42 analysis, 85% of APTs leverage DNS for stealthy command and control operations and data breaches as well. Why? But DNS protocol is a major blind spot to compromise the networks. DNS is a foundation and backbone for internet. I would say every cloud environment relies on DNS for service discovery, and it's the first packet which every LSN protocol sends. But when it comes to command and control and stealthy communication channel, it becomes extremely damaging. It's unencrypted by default, and basically it has logs are rarely monitored on the firewall. Firewalls always have the ports open for DNS, and the most important factor is stateless. And because it majority runs on top of UDP, it can be easily controlled from throwaway infrastructure. This is a diagram how it shows basically a standard DNS deployment topology. We have the local firewall and external firewall, both of them having DNS ports open. The main attack vectors when consist of DNS are DNS-C2, DNS tunneling, and raw exfiltration. The main purpose of all of the three are embedding in exfiltrating data inside subdomains of the DNS. DNS-C2 being the most damaging, all of them being done with fileless implant. In DNS-C2, the attacker embeds commands, and the main focus here is persistence and advanced persistent threat to rely on the system for prolonged period. Tunneling is similar. The only difference is tunneling tunnels the other protocols through DNS, which are blocked on the firewall. And raw exfiltration is the most simplest. It's a simplest single communication. It just exfiltrates, and the malware kills itself once a large amount of traffic is exfiltrated. This diagram shows how it works. It's a multi-stage process. Attacker registers a domain with a C2 server. Once the domain is registered, it generates a fileless implant. That implant gets delivered onto the endpoint. After getting delivered, it asks the remote C2 infrastructure with a query, sends a DNS queries in a beaconing pattern, what next command it should execute. So it's called as a pooling mechanism. The C2 server, it passes through the firewall, reaches the C2 server, the C2 server responds back, and the attacker executes that. The implant executes that command. But when it comes to, it's not just exfiltrating files. These commands are most damaging. It's not just data breaches, it's the next channel for delivering zero-day attacks. Some of the major damaging attacks, command and control can facilitate our remote code execution, shellcode exploits, and file corruptions. The attacker's purpose here is not to exfiltrate data, but damage the endpoint and spread laterally in the network. Other are side channel process abuse and persistent backdoors, and port forwarding and pivoting are some of the other factors. And Specifically, when it comes to rootkits, Terla is one of the APTs which use this. But the attacker doesn't have a bigger headroom when it comes to amount of data it can put inside DNS. DNS has some specification limitations when the amount of data it can be put inside the query section. Usually, DNS allows, for a UDP, basically, DNS allows you to have 255 characters max, 127 labels. A label is anything between a dot, and 63 characters is allowed per label. The number of questions are usually 1 per DNS packet, because most of the DNS servers don't allow multiple questions. And this is a standard DNS question format, how it looks like. It has a query name, query type, and query class. But what makes the actually DNS packet contain the C2 commands and exfiltrated data? Usually, attackers are trying to embed a command into the subdomains. They always try to encode and encrypt with different mechanisms, some of NetBIOS, CRC, hex. This always adds an entropy in your query name. Longer excessive labels. It's an option, basically, for the attacker to have multiple smaller chunks of labels or a label which is longer in length. And then finally, DNS is a restricted set of ASCII characters. Their words doesn't make any sense. They have non-dictionary tokens and DGA-generated style. But one thing I would say, attackers just don't register. When it comes to C2, attackers or APT botnet groups just don't register a single domain on a DNS resolver or an IAM provider. They deploy a fleet of servers for maximizing evasion. This diagram shows how the C2 infrastructure is scaled, and the higher the scale, the more the evasion is. So you could see on the right, you have all your enterprise networks which can be geographically distributed across different regions. You have redirector fleets. Redirector fleets are meant for evasion. They are specifically used to hide the C2 server's location. For L3 bot, it can be thought as a proxy chain. And the actual C2 servers are the dedicated C2 servers which register domains across different domain providers or domain registrars. And so that they can have maximum evasion. And they categorize themselves as a short-based C2 or a long-based C2 based on whatever the beginning pattern they exhibit. DGA is domain generation algorithm is just not layer 7 mutation. It's paired with IP mutation that makes them more evasive. That because eventually they generate algorithmically thousands of domains. One domain got blacklisted. They have other domains for that implant to query. And each domain usually also has multiple IP address so that the implant can load balance itself when querying or sending DNS C2 commands. And that makes your static blacklist evade easily. And there's hard-coded and algorithmically generated, so that's also adds evasion mechanism. There are 4 main types of domain generation algorithms, time-based and seed-based being the most easy to detect, while word list and characters are usually harder because of the pseudo-random generators, pseudo-generators and the word list DGAs they use. Some of the examples are like once you get a monotonic time clock, you can easily detect what the next DGA will be. But seed is the same. Once you grab the seed, you can understand what's the next DGA pattern it will be. But word list is difficult to guess. Moving on to existing approaches. Right now, there are 2 main existing approaches being used. First is semi-passive analysis, and second is passive analysis. Semi-passive analysis is less common. It's done with programmable software switches, also which use deep packet inspection as a middleware inside the switch. And that query, if it cannot find, it clones the packet to the controller. It replicates an SDN topology, how virtualization works in the cloud. But majoritarily, passive analysis is used, and the main factors are anomaly detection and thread signatures and domain reputation. This shows an entire flow of a network intrusion system from start to end. You have all the endpoints. Endpoints are sending all the sensors. They have running at the endpoint. They are sending all the aggregated DNS data. That DNS data is aggregated and passed to as a filter over a specific window. That window then runs to a stateless analysis. A stateless analysis then triggers a response which blacklists the domain in response policy zone. It's not always the case, but because it doesn't have physical access to the wire, it aggregates it into a log aggregator or SIM. After that, it generates runs stateful feature analysis and classifiers and machine learning models on it, and detects outliers. And that's where your SOAR pipelines and all that triggers, and outliers are blacklisted. The domains are blacklisted in response policy zones, and alerts are triggered. And it basically tells the EDR agent to start blocking that domain. The main challenges here are it is slow detection and slow response, specifically with the evasive nature of the evolving C2 implants. because the amount of time it takes to detect something and then reinforce the C2 implant has already mutated and started using a different domain. But if it's a zero-day attack, it may have already executed that command and started a child process or any other thing that may already execute and compromise your nodes. Then again, it's kind of a proactive mechanism rather than a reactive mechanism when it comes to C2 infrastructure attacks, and robust protection against domain generation and IP mutations. And if it's a passive analysis that's rarely used, it causes latency on the traffic because traffic has been mirrored, and that causes unwanted latency. And dynamic thread patterns. C2s are not just meant for standard web patterns. They are used for dynamic, like they use different query classes, text, MX, null, different timing, stealthy patterns, so that all the statics are broken down. So the proposed solution and the research which I will be talking about is, rather than being a proactive, it should be a reactive. So rather than the network hunting, once the C2 activities are executed, let your endpoint agent hunt what's happening, and that too hunting should be done inside the kernel at ring 0, where no user land evasion can hide from all these C2 malicious, irrespective when they are sending a packet. So bit background, how it can be done in Linux kernel specifically. It can be done using kernel modules, but I'll specifically talking about eBPF. eBPF is a modern way of reprogramming the Linux kernel in a safe way. It can be thought as a virtual machine running inside the Linux kernel, which allows you to inject runtime programs which get attached to the core kernel subsystem. So these diagrams actually show how it works. We have an eBPF loader. That loader gets compiled, and then bytecode is generated. That bytecode gets injected through BPF syscall. It goes through eBPF verifier, just-in-time compile optimizes it, and then it gets attached. Some of the core kernel systems are like Linux kernel network stack, kernel LSM, Linux security models, etc. The main factor here you could see is it has eBPF maps and ring buffers or perf events. These are the factors crucial when it comes to endpoint security. This gives threat and intelligence to the endpoint agent in the user space, what's actually happening inside the kernel. So just to summarize it, the user space can actually contact that eBPF maps and read what it's a custom BPF bytecode, and it's CPU architecture agnostic. Before moving deeper into the EDR agent, I would like to talk about what core kernel subsystems the EDR agent utilizes, starting off with the kernel network stack, which is also referred as a kernel data path. This shows the standard way how packets actually flow from user space downstream to the network device driver. User space system called the TCP/IP network stack, net filter, final traffic control, and the network device driver. These are all the hook points which eBPF allows you to inject the kernel programs, and some of them are kprobes, trace points, cgroups, etc. The main focus for the EDR here is BPF kprobes. Kprobes and trace points are attached to process schedulers. This helps the EDR to hunt if the agent C2 implant is forking itself and spawning child processes. It should not evade the detection. It should always get the parent process what's tied to it, and also helps in process hallowing and other shadowing mechanisms. Cgroup socket maps, it's used for monitoring DNS socket creations and all that events. Traffic control utilized specifically for quality of service in the kernel, but this specifically uses deep packet inspection. Here's where it raw passes the DNS questions inside the kernel from the SKB, also referred as socket kernel buffer, and then it runs enhanced intelligence on top of it. But eBPF allows you to inject all the custom programs, but the runtime integration should not compromise the integrity of the kernel, and the kernel should remain the most trusted execution environment in your system. And that's where LSM is used. LSM is Linux security modules. It's a mechanism which helps in order to ensure that every injected program is verified and integrity is ensured. And it interacts with kernel keyring and Linux security modules as other components for verifying the integrity with the custom certification authority the EDR agent generates. I'll talk about the main, what I call it as kernel-enforced endpoint security, and an extension mechanism for DNS. It's an agent-based endpoint security similar to your sensors running at the endpoint, but it's a multi-layer security. Starting off with the user space, it has eBPF agent. The agent is nothing but a loader, which I talked about before, which loads the eBPF programs. It has caches. The caches usually hold the top-level domains of the most world's reputed domains in the because the C2 server cannot get access to those zone files. Then it also holds a quantized deep learning model. A model it's used for data obfuscation detection mechanisms. And some metrics exporters is used to export all the kernel ring buffer metrics, which the kernel is exporting. Coming down to the user kernel layer, all those eBPF hooks are injected in runtime by the EDR agent, which I mentioned before. And your kernel is resilient now to tackle that. And basically, you could see all of them are contacting to the same eBPF maps. The eBPF maps becomes your system state store for storing all the eBPF information which each of the program is executing. So let's, to walk through how it works, let's assume that an implant C2 implant got infected and started sending malicious DNS packets. It sent down a DNS query downstream to the access control layer. It hit the syscall layer. Once it hits the syscall layer, the main focus of it is what's the process tied to this packet, and go and hunt for the parent process to it and make sure that the lower layers of the kernel gets the parent process only. It goes downstream, and then it hits the network stack. In network stack, what it does first it checks that is this packet process coming down, the packet coming down, is the process blacklisted? If not, it does the deep packet inspection on it. It's not always assured that the kernel restrictions will allow you to perform enhanced lexical analysis. That's where it basically has two options, that it redirects or clone redirects the packet, where packets are redirected live from the kernel to the user space. The EDR agent sniffs it continuously, but before doing that, you could see it updated the process telemetry in the maps before doing that. The EDR agent in the user space continuously once it gets the packet, it knows that the corresponding maps have been updated. It gets the process level information and does all this inferencing, which is data obfuscation detection mechanisms for randomness. Post doing that, if it found to be malicious, it goes and blacklists that process in the eBPF maps. This forces the implant to retry. So the implant retries, and then it passes through that, but now the process is blacklisted. It kinds of creates a trap for the implant. And this makes it retry again and again. But the kernel is exporting every rich telemetry to the user space, and this messes up their beaconing pattern. If the implant is beaconing, then it beacons again with a jitter or exponential backoff mechanisms. And eventually, once everything, the EDR agent collected rich behavior from that implant behavior, it goes and kills it, and the implant is terminated. So to summarize, it's a continuous security enforcement loop happening between the kernel and the user space, where the the eBPF program in the kernel is helping the user space. User space is reprogramming the kernel security layer, and that continuous enforcement loop continues until the implant gets terminated or it's killed itself. There are two main modes I would like to talk about. It works. These modes are replicated how real-world C2 attacks, C2 tools exhibits when their communication is broken down when it comes to the DNS. The first mode I'll talk is active process security enforcement mode. This is meant for endpoints which want absolutely no data loss, no command execution, but can tolerate some latency. This is a brief detailed information. So eBPF maps, I'll talk about eBPF maps. Other components are the same, which I mentioned before. The first eBPF map actually holds the DNS query ID as the key. It's a hash map, and the value is stored in the kernel memory. And the value is the system monotonic time and the process information and thread information. The second map holds the monotonic time and the value as a scan. I will talk why a second map is used. Same process, I'll walk through that. The packet is sent, hits there, raw passes it, does that inference. Now it redirects the packet. This only works for UDP, by the way. If the DNS is transferred over UDP, it redirects the packet, and if it's malicious, it gets robbed. But yeah, after the endpoint agent in the user space reads it, it infers through its caches, whether it's a top-level domain or already inferred, runs an inference on top of it. Whatever the verdict is, it makes sure that the packet which came now, it gets from the map, the first map basically, process scan time and the process information. And then that information, if it's malicious, that telemetry which the eBPF program, the kernel updated, is used to track the activity of that malicious implant. Post doing that, if it's a benign, the packet has to be resent. And that's where it sends the packet, it authorizes the second map. The second map is especially used for zero trust enforcement, because when the packet is redirected to the user space, the malware should not brute force itself and understand and guess the time, okay, when next packet will come, then security, that should not happen. So this monotonic time is system nanosecond accuracy, which kernel uses non-maskable interrupt safe time. So it has precise timing and brute force attack prevention. Packet is sent down back, and now the kernel again verifies whether this packet coming is authorized from an authorized sender, and packet leaves. And this process continues again, and eventually, once enough telemetry is created, the implant is killed. The second mode is it's not always possible to redirect a packet. It won't ever work for TCP, will cause unwanted congestion, and any redirection to a different Linux network namespace or a network interface raises an interrupt causing latency. So it's not always feasible. That's where a second mode I want to talk about. I'll talk how it works in a state diagram. Your C2 and tunneling starts, the eBPF, it hits the traffic control layer, the eBPF program starts the packet inspection on it. Now it doesn't redirect, rather it clone redirects the packet. That is internally kernel cloning the entire packet in the traffic control layer, and that packet is sent back and also expose the process telemetry. Once doing that, the EDR agent does a deep learning model inferencing on that cloned packet. Post doing that, if it finds that there is some malicious embedded commands inside it, it keeps on tracking the exfiltration and C2 tunneling attempts in user space. It's done in the user space memory, basically. Once tracking everything, the implant again retries. Same thing happens. It clones everything. Again, it finds the event tracking in the user space is incrementing. Eventually, it found some behavioral analysis that the same implant is exhibiting multiple patterns, the same process, by the way. It goes and updates a map, the eBPF map, saying that this process is potentially a malicious one, and it should start, the kernel should start dropping. So now the kernel transfers the eBPF programs, basically reprograms the network stack, and then eventually you could see the eBPF kernel program starts hunts if the process is blacklisted, because the implant again retried now. And the same thing, the kernel program starts starving or basically starts dropping the traffic. This, again, same thing I mentioned, messes up their seed beginning pattern, but it keeps on cloning the packet, so you have richer behavioral analysis. Implant retries, same thing happens, same thing is collected. And eventually, once everything, rich behavior is analyzed, all the analysis, it goes and blacklists the domain, and the implant is killed. Everything of this depends upon the accuracy, because the model, if the model is not accurate, can eventually cause service disruption. It can kill benign process. So the model uses a dense neural network-based data obfuscation detection model. First, I'll talk about the features. The Linux kernel features, these are used for deep packet inspection, and they are nothing but limits. This limit specifies what is the maximum and minimum range you want, and anything above that range is considered as malicious. Between those minimum, maximum is considered as suspicious. Anything below is benign. In kernel, they are actually user space features. The features are used for enhanced lexical analysis. They are some, again, the characteristics which are talked about, about query patterns and lexical measures. They are the same lexical features. But I want to talk about entropy here. Entropy is specifically used with the Shannon's entropy with a base logarithmic 2, because DNS only allows ASCII characters, as restricted as Sky said. I'll talk about the model architecture. But before talking about the model architecture, I'd like to talk about data sets. It was a 60 million domain data set, close to, and it was synthetically generated utilizing ISP real-world traffic and the traffic from exfiltrating various files and executing different malicious commands from open source adversary emulation tools. This represents an ONNX graph. ONNX is Open Neural Network Exchange. It's a way of serializing deep learning models. It's meant for faster inferencing and lower memory footprint. And you could see and again, it's quantized, because floating point arithmetic usually takes CPU cycles. So it is converted to a lower precision for faster to match the speed of the EDR and the kernel processing. It's a one input layer, 3 hidden layers, 1 output layer. ReLU as an activation function, sigmoid for binary classification. But each of these modes can be worked, and can safeguard your endpoint from this C2 implant. But C2s are kind of a dual-sided, where if you want to safeguard a cloud infrastructure, the C2 implant also has to be killed as early as possible, as well as your firewalls and your cloud infrastructure should be made secure, so that this remote scaling C2 infrastructure is broken down. This is a standard deployment architecture I would like to talk. This assumes it's only in one AZ, but it can scale as horizontally as required. So you have all the data plane, and the data plane has set of these eBPF agents deployed at the endpoint. And before talking about the actual framework strategy, I'll talk about the DNS topology usually looks like. You have a local authoritative DNS server with a party, with any backend it is. It can be LDAP provider for your cloud, or it can be managed DNS authoritative server, or it can be a Postgres if it's done on-prem, or any generic RDBMS backend. It has forwarded to a recursor, which is a resolver upstream forwarder to the upstream DNS servers, a DNS firewall connected to a network firewall, internet gateway, and forwarded upstream to the actual DNS resolvers, whatever the upstream forwarders are. But your IPS and IDS are connected, and you have all the same everything ready. But now these eBPF-powered agents now are running, and let's assume, if I walk through this flow, let's assume this agent, this one data plane node got infected with this C2 server. It started sending malicious packets, and let's assume this is the IP it's sending, and this is the domain exfil.com, and there's some random thing it's asking what, or it can be doing commands, running commands. Post doing that, the implant, whichever mode, the EDR agent, whichever mode it's running, in active or passive, it kills it. But it gathers all the rich telemetry. It exports everything in a form, it streams everything collected from the kernel eBPF ring buffers into a message broker. A message broker can be a topic. It can be even a queue, anything, and our managed cloud provider service. Suppose that there are a set of controller nodes. These are specifically used for dynamic domain blacklisting to combat DGAs. They consume that, and then the controller servers ghost and blacklist the domain in RPZ dynamically. Post doing that, it goes ahead and also asks the upstream DNS resolver, where is this located? This is specifically meant for reverse hunting to analyze the redirector's nature. What's the redirector IP nature? How is the C2 infrastructure pooling and proxy chains are working when sending different IP addresses? Post that, it sends back, the controller streams back all that, and then each of the data plane eBPF agents consumes those events, and they update their malicious caches, which I talked about, the user space cache, which is, and it also injects security filters inside the kernel. So your entire data plane now got safeguarded from exfil.com domain, and there was nearly no data loss, and you combated the DGA specifically. And even though that implant mutates and migrates, it's not going to survive because that domain is dynamically getting blacklisted. But the benefits of this is it has a dual-layer defense. For example, if one of the endpoint is running a lower version of Linux kernel which doesn't support eBPF features, or it's running a different OS, you made the DNS server resilient, and that DNS server got reprogrammed. So eventually, if other OSs, that same DNS server is going to protect your endpoints. And then finally, the rich telemetry is exported by the eBPF agents to your SIM. So everything is exported to the SIM. So I'll show a demo right now of Sliver or Bishop Fox Sliver tool. And for that demo purpose, I have a on-premise infrastructure, and Kafka is being used as a message broker, and I've already generated, and PowerDNS is used as an DNS server. I've already generated all the domains in the domain DNS server, and it's using word list strategy. So after doing that, I start the Sliver server. I'll show some of the attack first, and then I'll start the agent. So I just start the Sliver server, and I then generate the implant. I just transfer the implant. It can be done through any infiltration mechanisms. Post that, the implant started running, and you could see the logs here. It started querying, and you could see the commands are being embedded like this on repartition.com's domain. Now, once it's done, I'll start first with selecting the session. So I'll start the session. I started executing remote commands on it. Some of them, like get URI and other remote commands I'm executing. I'm also showcasing a port forwarding mechanism. So I'm port forwarding Nginx server on 3200 port. So yeah, I did forward that. So it generated a large volume of DNS traffic because it's a session-based, not a beacon-based implant. So push. Anyway, so once that is done, I start a reverse shell on it. And once the reverse shell is started, I start the endpoint agent. Once the EDR agent starts, it injects all those eBPF programs. Once the eBPF programs are injected, it immediately started detecting everything, and it started asking the deep learning model what should be done for it. Post asking it, you could see it will start, now the implant started getting query errors immediately because the kernel EDR agent started dropping it. First read, so you could see there's a query error. Then this will again force it to retry. Yeah, so again it retries. The behavior is captured here. And you can see it's 409711 is the process which is actually doing that attempts. And eventually, once there's enough telemetry, the EDR agent goes and kills it. But it captured all the rich telemetry. So it's exporting right now to Prometheus and export visualized to Grafana. It can be any SIEM or ELK stack, any cloud provider stack. So it tracks how many packets were redirected live from the kernel. It tracks per process level information. Like for this process, for this thread, it was exfiltrating 4 times how much time the process was alive. So you could see it shows the process alive time as well as each individual packet it was trying to send was actually seen in the dashboard with eBPF and ring buffers, everything exporting it in real time. And everything got exported into Kafka. This is the same thing, basically. And it got domain got blacklisted. As I said, RPZ is party Postgres, so it got blacklisted. So just a metric about data response speed. How fast is this when it compares with and precision? So when we're talking about the response speed, it's usually for active mode for 10 exfiltration attempts. The x-axis shows the attempts per attempt, and y-axis shows the time it takes to respond to it. On average, it takes T26 microseconds for every exfiltration C2 attempt. And this shows this shows the F1 score precision recall graph. The precision for this model was around 99.89%, and the main focus here is to reduce the false positives. So 0.7 was the threshold kept as a binary classification. Anything above that is malicious. Next steps. These are the steps which are actively worked around right now on this project, which is right now it works for DNS, but I'm currently working on for TLS fingerprinting. Well, TLS can be done in 2 ways. One is user space TLS. Most of the TLS is done inside the user space, but there are other encrypted tunnel mechanisms like WireGuard and IPsec. Both of them are done through core kernel components. So attaching TLS fingerprinting mechanisms through eBPF can help hunting down that. Process correlation. Well, this is the next advanced mode, I would say. For example, this is useful if the implant was initially trying to send through DNS, and then it started sending through HTTPS. You know the process in the eBPF map. You know the deep system telemetry, what the process inside happening in the kernel, so that can be correlated. Continuous model evolution. The model can easily get obsolete with a new data obfuscation. If a new obfuscation comes which looks very much similar to like normal English words. In that case, there's continuous learning and detection, confidence-based learning approaches, but I specifically want to talk about GAN plus LSM. GAN specifically for poisoning, so that the more obfuscation formats the model can learn. And LSTM is for behavioral analysis specifically. Right now, the behavior is just like you have 3 or 4 continuous attempts per process, go and kill it. But there can be richer behavioral analysis from the kernel eBPF maps done through LSTM and RNN approaches. And finally, DDoS protection. There's ghost attacks and flood also as a tactic being used. So eBPF can be injected over the entire kernel network stack. So it has a support for HTTP, Express Data Path over the network device driver, which is the very lowest layer of the network kernel stack. You can have DDoS protection mechanism so that it inherently just not becomes an endpoint security, it becomes an endpoint security, ingress endpoint security solution as well. So it just doesn't prevent exfiltration. Key takeaways. When AI is paired with eBPF, it matures your EDR. Because eBPF helps you to reprogram the kernel. It helps you hunting deeper system telemetry. And it eventually matches your user space EDR with richer behavioral metrics. And it can, even when paired with AI, the dynamic kernel enforcements, which the AI can put, the model can, EDR agent can put, makes it resilient. Then talking about the DGA, breaking down DGA, kernel-driven EDR and cloud firewalls. So I think like it can be, if you want to break down the remote C2 scale, it has to be like a bottom-up approach where your operating system makes the EDR mature, EDR makes your SIEM mature, and that SIEM eventually firewalls, and that firewalls dynamic blacklisting for L3 and L7 filters on the firewall makes your firewalls intelligent and your cloud network is secured from this remote mutative C2 infrastructure. Irrespective, they change their domains or they change their IP address, still the infrastructure is protected at a scale. And finally, this worked because DNS is unencrypted. And even though, for example, DNS over TLS is one or other encryption, like HTTPS, the most preferred one, or WireGuard, for example, in that scenario, you need behavioral analysis. It cannot be done just purely on lexical analysis because it may raise false positives. That way, here also the eBPF and the kernel enforcement can help to mature your SIM. The more deeper system telemetry your EDR agent exposes, the more faster the SIM matures and your SOAR pipelines become more faster to prevent these encrypted tunnel attacks. Thank you for your attention and listening to my talk. You can reach out to me through this email. The framework code base is open source and can be found here, as well as a white paper. This is a graduate thesis being published, so it can be found here. If you have any questions, I'm open to answer them. Thank you for your time and listening.